Welcome to The Explainer. Today, we're unpacking a genuinely fascinating challenge from the world of computer science. How exactly do we teach computers to reason like human experts? When we look back at the foundational academic research, specifically the work around formal specification languages in the 1990s, we uncover the invisible blueprints that actually helped shape artificial intelligence as we know it today. It's a thrilling journey into the very architecture of thought, so let's get right into it.
Okay, so here's the core dilemma. For decades, we absolutely knew how to feed computers raw data, right? We knew how to give them straightforward computational tasks. But how do you give a computer intuition? How do you give it the gut feeling and the complex heuristics of a seasoned professional? How do you actually encode a doctor's diagnostic instinct or an engineer's design philosophy? Well, it turns out encoding human intuition is a completely different ballgame than just asking a computer to sort a spreadsheet.
Think of traditional software engineering kind of like a restaurant menu. It specifies the what. You tell the system what functionality you want, like calculating payroll or sorting a massive database, without necessarily worrying about the human-like logic of how it gets done. But knowledge engineering, that's the recipe. It requires capturing the complex how and why of human problem solving. We aren't just asking for an output here. We are demanding that the computer accurately mimics the nuanced reasoning process of an expert to arrive at that output.
So, here's our roadmap for this explainer. We'll start with a knowledge software challenge, run through the 4 rules of AI, check out the CADS blueprint, compare formal versus executable languages, dive into designing with desire, and finally, zoom out for the big picture.
Part 1. The Knowledge Software Challenge. This is where we really see the historical split between traditional software and knowledge-based systems. In standard software, if you have a clear requirement, you can almost always write an efficient algorithm to solve it. But in knowledge engineering, you literally can't just algorithm your way out of a complex medical diagnosis. If a patient comes in with overlapping symptoms, there's no simple magic mathematical formula to spit out the answer. Instead, solving that problem relies on domain-specific and task-specific heuristics. Essentially, these are the hard-earned shortcuts and rules of thumb that a human expert develops over, say, 20 years of practice.
Moving on to Section 2, 4 Rules of AI. To capture these incredibly complex human heuristics, researchers had to establish a completely new set of ground rules for building knowledge-based systems. Rule 1. Separate knowledge from control. The actual facts the AI knows must be kept completely distinct from how it manages and searches through those facts. Rule 2. Create generic problem-solving methods. This way, you can reuse a diagnostic strategy across totally different fields. Rule 3. Define an object meta-relationship. This means the system needs a higher meta level that supervises its base object-level knowledge, like a manager overseeing a worker. And Rule 4. Combine functional and non-functional specifications. The system needs to know not just what to do, but functionally how to execute the algorithmic control to get there.
Section 3. The CADS Blueprint.
So CADS became one of the absolute most prominent frameworks used to actually model this human expertise into a structured format. Think of it as a beautifully clear, layered cake of reasoning. In a medical diagnosis scenario, it's split into 3 distinct layers. At the very bottom, we have the domain layer. This is your raw, static data, the symptoms, the diseases, the basic causal relationships. Moving up, we hit the inference layer. Now this is where the magic starts. It takes those raw symptoms, generates possible hypotheses, and then systematically selects the most probable diagnosis based on expert preferences. Finally, at the very top is the task layer, which defines the ultimate goal and directly controls the execution of all those inference steps.
All right, Section 4, Formal versus Executable Languages. Now you might be wondering, how do you translate that CADS conceptual blueprint into actual computer code? Researchers faced a major choice between 2 totally distinct languages, the highly theoretical language known as ML2 and the deeply pragmatic CARL. Think of ML2 as the strict mathematician. It uses highly expressive first-order predicate logic and complex dynamic logic. It's incredibly precise on paper, and it's evaluated purely through theoretical theorem proving. But you can't easily run it on a machine to see what happens. On the flip side, we have CARL, the pragmatic builder. CARL actually restricts its expressive power, using a simpler variant called horn logic. Why? So it can be executed. With CARL, you can actually run the specification and use operational testing to see if your system reasons correctly in practice. It's that classic trade-off, absolute mathematical perfection versus practical, on-the-ground execution.
Section 5. Designing with Desire.
CADS wasn't the only game in town, though. The Desire framework essentially tosses out that strict 3-layer cake of CADS and uses what's called a compositional architecture.
This just means breaking the system down into interacting modules. Honestly, I like to think of Desire as the ultimate corporate delegator. Instead of layered global rules, the entire system is a network of specific worker and manager modules. Each module has its own internal object-level knowledge and its own meta-level boss controlling it. The system functions through these complex transactions between independent, highly specialized departments.
It's a really clever setup. Desire elegantly handles data flow through 4 specific transformations. You have object interaction and meta interaction between the different modules. But the really fascinating parts are upward and downward reflection. Upward reflection is when a module's meta level stops and analyzes its own object-level facts. Downward reflection is when the meta level takes the results of that reasoning and forces the object level to act on them. And when you look closely at the specification of a single reasoning module, you see exactly how tightly it controls the reasoning process internally. It is just an incredibly robust way to build a complex, multifaceted artificial intelligence.
Finally, Section 6, the big picture.
So what does this all mean for us today? How do these 1990s academic blueprints relate to the grand arc of technology? Well, as Brookings noted way back in 1986, analysis is not simply interested in what happens, but also with how and why. That quote summarizes the entire ethos of knowledge engineering. We don't just want an AI to give us a magic answer. We want it to possess a verifiable, structured rationale. The frameworks we've explored today, CADS, ML2, CARL, and Desire, these were the pioneering efforts to capture the intangible, messy reality of human expertise and bolt it securely into a mathematical, logical framework. They laid the groundwork for making an AI's thought processes visible, structured, and completely intentional.
So, I want to leave you with this provocative thought. Today, we're dealing with massive neural networks that often act as total black boxes. They give us incredible answers, but they completely hide the how and the why. As artificial intelligence becomes infinitely more complex, penetrating every single aspect of our lives, how are we going to specify the invisible blueprints of tomorrow's AI? Will we have to return to these rigorous, transparent structures of knowledge engineering to ensure our machines are actually reasoning the way we want them to? Thank you so much for exploring this fascinating topic with me on this explainer. Keep questioning the blueprints, and I'll see you next time.